Notice this. When it comes to E2, E2 is a single step reaction and its molecularity is 2. What does that mean? Is this, suppose if you have, let's say, a chloride here like this, and if I treat with something like alcoholic KOH, which is usually observed as a strong base, and if this is facilitated with heat, you know that heat will always increase or enhance the elimination part, and it will give you two products like this one and another one is this one. All right, these are the two products you will get. Now since it is only happening in one step, right, so this will become the rate determining step as well. And in this one step, if you notice, it is dependent on two reagents, two basically reactants. One is a substrate, the other one is a reagent. And in a slow step, the number of molecules involved is termed as molecularity. So the molecularity in this case is 2. And it is a single step reaction and the molecularity is 2. Is that point clear? Now, if you notice the rate of the reaction, rate of E2, how do I write? Rate of E2 will be equal to some constant into substrate concentration here, which is alkyl halide, into reagent concentration here, power 1 in both the cases. So K into Rx into base concentration power 1 and 1. So that's how you will get the order of the reaction as 2. Okay? Here the order of the reaction is 2. Next. And you could see the same reaction. I have written it down here. OH could have removed proton from beta position at this beta position or this beta position, which leads to formation of two products. If you notice these two products here, this double bond is surrounded by three alkyl groups, while this double bond is surrounded by only one alkyl group. And more the number of alkyl groups surrounded, you call that as Shezhev product. Less the number of alkyl groups surrounded, it is called Hoffman product. So you might get a Hoffman product and a Shezhev product. If the stereochemistry of this molecule is not mentioned, that means whether it is bulky, whether it is R configured, S configured, nothing is mentioned, then your usual thing is always go with the stability of the molecule. In this case, Shezhev is more stable, so that is major. But is it always going to be major? Not necessarily. Okay. Now notice from here we could say that more the substitution present on the alkyl group, more stable the alkene you can get. Makes sense? You can get a more substituted mean more stable alkene. Therefore, more substituted alkenes like this, if you have chlorine with phenyl, chlorine, CH, CH3, CH3, this will produce a very stable alkene because getting a double bond here, you'll get a very stable alkene. Next tertiary, next this one, next primary, next completely ethyl. Okay, this is how the rate of E2 goes. And interestingly, E1 also goes with the same fact because E1 is more about stable carbocation, E2 is more about stable product. And both of them are leading towards the same side only. So whether it is E1 or E2, they always favor more substituted groups. Next. Stronger the base, it will highly favor E2. Reason being, it would never let the molecule to go in the route of carbocation. The minute it is trying to go in the carbon, immediately it will pull out the proton and try to convert into double bond. Therefore, stronger the base, better it is. NH2 minus, alcoholic KOH, RO minus, tert-butoxide, LDA. LDA is this lithium isopropyl amine. Okay, that H minus, triple bonded C minus, R minus. These are strong bases, and these strong bases favor E2. The strong bases favor E2. Okay. E1 is always favorable in weak bases. That's the major difference between those two. Got it? Because you need to make a carbocation is formed first. So to keep that carbocation formed, you will give some time to it. Okay. Right. Next, polar aprotic solvent is favorable here. Polar aprotic solvent. What are the polar aprotic solvent? Anything which is ether, which is ketonic form, which is DMSO. Okay. DMSO is this one. Double bond, double bond O. Sorry, this one. This is DMSO. That is dimethyl sulfonyl oxide. Got it? Then DMF. That is HC double bond N with two methyls. So this is DMF. This is DMF. One is DMSO. The other one is DMF. Then we have this kind of cyclic ethers. Got it? Now all these type of compounds would be favoring E2 a lot. I mean, basically these are all the solvents. In this solvent, E2 is highly favorable. If you notice the very similar case we discussed, right? Wherein it is favoring in the presence of an aprotic solvent. Got it? Same logic happens here also. Now, notice this. Next, anti-elimination. Here in E2, it will always prefer an anti-elimination. What do you mean by anti-elimination? You see this. If you have a CH2 group here, CH2, CH2 here, and on from this end, imagine chlorine is leaving. Okay. So from this end, this is chloride. This is chloride formed. Okay. I'll keep it little colored here. This is chloride. The yellow color one is a chloride orbital. Okay. And opposite to that, we have an carbon connected to this side. We have carbon connected to a hydrogen. Okay. This I'll color here. This is hydrogen. Okay, beta. Now, if of course there are other two hydrogens which might be like this, that I have not written. Okay. The one which is opposite to this orbital here, it will help the base to pull more easily. Base is B minus, which is coming with a pair of electrons. Okay. Now, when this base is extracting this hydrogen, simultaneously, if this halogen is moving away, correct? And all of them are present in same plane. You notice that these are all present in same plane. Okay, this base orbital, this hydrogen orbital, this carbon, this orbital, and this halogen orbital. If all of them are present in the same position, then the chances are you will notice that this will start moving away. This hydrogen will start moving away. You will see this double bond is forming simultaneously, and this chlorine is moving away as well. So this is going as minus, this is going as plus, and this has been pulled by a base which is having delta minus. Done. And after removal of that, we will get this as CH2 double bond CH2 plus Cl minus plus Hb. Done. This is how the product will be formed. So that's what I am trying to explain here. So it will favor an anti-elimination. Okay. And you know that in case if you have this molecule here, correct. Now notice this one. If alpha carbon is this one, so then beta carbon is this one, right? And on beta carbon, you have hydrogen also, you have deuterium also. And which bond is weaker? Hydrogen bond is weaker, deuterium is stronger. So if a base comes, it will try to extract hydrogen first, more than deuterium. And simultaneously, Br minus will leave. Okay. So if I at all I have to perform elimination here, I have to remove Br here and H here. And how are they both aligned better? Both of them are on the same side. Okay. If the removal groups are on the same side, that is called erythrokind, right? erythrokind. This is an erythrokind. And erythrokind, you are performing an anti-elimination. Correct? What do we get here? You know that we will get the same form here which we discussed earlier. This is E erythro. Okay. So you can see erythro, if you perform anti, you will get trans. Got it? This is what we learned for addition, right? This is the form we learned for addition. This is addition formulas. What is the addition formula? Cis plus anti will give you trio. Trans plus anti will give you erythro. Trans plus anti, sorry, trans plus uh, trans plus sin plus will give you trio, and cis plus sin will give you erythro. This is the form we learned for addition. What will be for elimination now? It should be exactly reverse of it. That is, trans performing an anti should give you cis. Not trans, trio. Erythro performing an anti should give you trans. And trio performing a sin elimination should give you trans. Erythro performing an sin elimination will give you cis. Got it? So in this case, it is an erythro form. If at all I give you an anti-elimination, I would be able to get a trans form. Acha, how would I know how to put the trans here? See, these groups should be always opposite to each other, and these two groups should be opposite to each other. So that's how you need to place the trans form here. Got it? Can it out here, beta?
No, sir.
Right. So if you have this molecule here, Br and H, if at all I remove that, same thing. This Br, this methyl should be opposite, H should be opposite. This is major product and both of them are hydrogens. So I can get this minor product also. Okay, where I could eliminate this Br and this H also, right? If at all I do that, what I'm performing, this will be threokind now. On a threokind, if I make an anti, I should get cis. Here, chlorine is present, coming out of the plane, and here methyl is coming out of the plane. If methyl is coming out of the plane, hydrogen must be inside the plane, correct? And if hydrogen is inside, chlorine is outside, then I can make an anti-elimination. So anti-elimination will favor on this direction. So double bond will form here. This side of the direction, you cannot get a double bond because hydrogen and chlorine are on the same side. We should have them on the opposite side to eliminate. Okay. Next, if you notice this chlorine here, removing this chlorine, this beta does not have any hydrogen. Only this beta has hydrogen. So you'll get only one product of elimination, that is this one. Clear? Next, if Cl is present here and already there is a double bond, correct? And left hand side there is no beta hydrogen and right hand side beta hydrogen is there, but it already has a double bond. Beta hydrogen should always be on the sp3 carbon. They cannot be on sp2 or sp carbon. So therefore, this does not give any elimination at all. Acha, would that mean there is no elimination reaction will happen? No, because E2 is not happening. So it will forcefully has to take the root of E1. So what is the E1 root, beta? You remove this chlorine from here, correct? You will get a positive charge at this position, isn't it? The positive charge can undergo resonance on both ends. Double bond can go here, positive charge can come here, correct? This is how you can get here. So once you get a positive positive charge here, then you will try to see whether the elimination is possible here or not. Okay. Now notice, if at all positive charge is here, is there any beta position hydrogen here? No. Is there any beta position hydrogen here? No. That means even E1 is not getting possible here. Even after making a carbocation, I'm still not able to find a route where I can make a double bond. Am I clear on that? Therefore, this reaction has no other sense but It cannot go not via E1 nor via E2. Next, suppose if chlorine is present here, there is no beta hydrogen here, there is no beta hydrogen here. So this also cannot go via E2 because I'm taking a strong base, I'm expecting an E2, but it will not go via E2. Okay. So it has to forcefully go via E1, which means first a carbocation will form, and then one of the methyl will shift on to this one. Carbocation will come at this position. After that, double bond can form here. So you can get this as major product, this as minor product. The major product is Shezef and minor product is Hoffman. Done? Now, in case of E2, there are certain special cases where only Hoffman product is favorable. Now see what are the special cases. First case is when you have weak leaving group. The leaving group is the part which is taking electrons and going away from the molecule. Like fluorine, halogens, these are all leaving groups. Now fluorine, Nr3 plus, Sr2 plus, Pr3 plus, OMe, OH, NH2. If you notice all of these are very, very weak leaving group. Got it? उसको आसानी से निकाल नहीं सकते because they will end up getting a strong base as soon as they relieve from there. If you remove it from here, F minus is a strong base. Nr3, a strong base. OMe minus, a strong base. OH minus, a strong base. NH2 minus, a very strong base. Can you notice that? So after removal, they are trying to become a strong base, which means that is not possible to generate that kind of strong base here. So in such cases, how does the mechanism favor here? Now, E2O minus will go here to extract proton. It will go here to extract proton. Now, what problem that will happen here is this one. See, while fluorine is present here and one hydrogen is present here, when you are trying to extract base from here, right? The double bond will try to push here. I mean, the sigma bond will try to break and convert into a double bond form here, and fluorine is leaving. But it will not happen simultaneously. As soon as the hydrogen is left here, as soon as the hydrogen is leaving here, there is sufficient delta negative charge already created before the fluorine could leave. Got it? This is the way the transition state would form. This is a transition state. Got it? Same way, if hydrogen is present here and fluorine is present here and base is trying to extract proton from here, then you will notice that this hydrogen is leaving with base but creating a delta negative here, then a double bond form and a fluorine is trying to leave by delta negative. Now, these are the two transition states you will get, TS2 and this is TS1. Between these two transition state, here you have delta negative at primary position. Here you have delta negative at secondary position. Which one is more stable? Primary position. Therefore, it would go through this route where you will get a transition state here. This transition state. Clear, beta?
Yes.
Therefore, this is a transition state through which it will go. Hence, that will become a major product here. And this happens with all the cases where there are weak leaving groups. Got it? So the Shezef product will be minor, the Hoffman product will be major. Okay, next. Notice bulky groups here. Okay. If there is a bulky group at gamma position, so you know that this is alpha, beta, and this is gamma. At gamma position, you will see there are three tertiary, I mean, it is a tertiary group there, or three methyl groups are present back to back here. In such case, even though this base is not very large in size, for this base to go and extract proton from here, this cloud will start repelling it. This total cloud will start repelling this E2O minus. So it becomes very challenging for E2O minus to come all the way here and try to extract the hydrogen. Okay, beta. So removing chlorine from here, removing hydrogen from here, converting into a double bond, this form will be difficult to make. So that's why this is minor. And this hydrogen does not have any such steric hindrance around it. So therefore, E2O minus can easily go and take away this H plus. Therefore, again, Hoffman is major here and Shezef is minor here. Correct? Hoffman is major. Done? The second case is clear. See the third case. Third case is when the base itself is very bulky, like tertibutoxide, LDA, trimethylamine. These are very bulky bases. Now, for such bulky bases, if you try to remove chlorine and a hydrogen from here, you will get a double bond here. Or remove chlorine and hydrogen from here, you will get a double bond on this side. So you would get this as minor, this as major. Again, same problem. The bulky groove becomes very difficult to go all the way into this groove and extract base. So it will always notice for the least substituted position from where I can pull the hydrogen. So therefore, Hoffman will be major product in this case. Clear, beta? So therefore, you might have understood that what happens in E2 cases. In all the E2 cases, when you need to think Shezef, when you need to think Hoffman, okay? So these are the cases where Hoffman is always favorable over Shezef. Next, let us see the next mechanism, which is E1-CB. E1-CB is a case where you have a conjugate base forming as an intermediate. How does the mechanism happen? Here also the condition is it must have a weak leaving group. So whatever the weak leaving groups just now I picked up, those are all going to be valid here. At the same time, along with that weak leaving group, the at the beta position, the carb anion which is forming must be resonance stabilized. Unlike the earlier cases, where if you notice here when I wrote, I did not write a complete negative charge here. I didn't write a complete negative charge here. Correct? I said it is a E2 mechanism, but E2 characteristic, carb anion characteristic is observed in this E2 mechanism. Okay? But it is not complete carb anion. But E1-CB differs there. In E1-CB, you will have a complete carb anion formation. Clear, beta? So here, you will notice that this is what I have written it. See, E2O minus, if at all it takes H plus from here or H plus from here, you know that Hoffman is major, and this is going to go via E2 with carb anion character, but not complete carb anion formation. But by chance, at this gamma position, there is something like a double bond O. Now what happens? E2O minus will extract H plus. First, a complete carb anion is formed. So an intermediate is actually formed here, which is a carb anion. So this is a conjugate base. Conjugate base has been formed. And once you get this conjugate base, this negative charge will push to make a double bond, remove fluoride from here, and thus converts into a major product. Is this clear, beta? So anything which has a double bond character which can stabilize this carb anion here. So if you have NO2 and I get a negative charge here, so that negative charge can stabilize on this left hand side. That's why the first step is conjugate base formation. And the next step is, alkene formation. So OH is a weak leaving group that will leave once the complete carb anion is formed, and then it will push afterwards this OH minus will leave. Got it? This type of mechanism is called E1-CB mechanism. Okay. And next mechanism is EI mechanism. EI means elimination internally. Elimination is happening internally. That means within the molecule. And Most of the time, whenever internal elimination is happening, it will always happen via syn type. So this is also called as syn elimination. It will happen via syn form. So therefore, it is also called as syn elimination. All right. Now, notice this one. How does this proceed? Check out via pyrolysis of ester. First example is pyrolysis of ester. Okay. Suppose there is an ester here. Ester has two parts, beta. This part is called acyl. The left hand side part is called acyl, ACYL. The right hand side part here is called alkoxy. Okay. That is alkyl group with an oxy. That's why it is called alkoxy. But are you with me? Right. Now, this alkoxy part is the one which will convert into an alkene, and the acyl part will convert into an acid. When would this happen? Just by heating the esters. Now notice, when you heat the ester, these two carbons have projected here. Now this first carbon, this is the first carbon, this is the second carbon. On the first carbon, hydrogen is present here, and on the second carbon, there is an oxygen which is connected to this C double bond O here, and which is connected to CH3 here, this way, correct? Now what you would notice here is there is a six-membered cyclic transition state forming. There is a hydrogen here, there is an oxygen here, and there is a double bond breaking up here, and there is an oxygen here which is breaking up, and then there is a double bond which is making up here, and then there is a double bond which is making up here, correct? This is how the molecule has been. So this is that transition state happening, correct? So this transition state is a six-membered cyclic transition state. So it will go through a 6 MCTS, okay? And thus, now notice what is happening. This carbon hydrogen is in the direction. Suppose if it is in this direction, on the same side of the direction, you will have carbon oxygen also. So this is breaking, this is breaking. So both sides there is a breaking happening, and both of them are happening on a same side of the molecule. That's why it is called syn elimination. Okay. Now, if by chance I have two different types of beta positions, now in this alkoxy, this is the alkoxy part beta, and that's where the alkene will form. On this alkoxy part, if there is a chance of getting two alkenes, I could get an alkene this side also, I can get an alkene this side also. If I get this side, it is a Shezhev product. If I get this side, it is a Hoffman product. And here you would notice Hoffman as major product. Now why that is happening, you notice in these two structures here. Suppose if at all I write this particular structure here, so I'll put the numbering here 1, 2, 3, 4. These are the numberings I put. Okay. So this is carbon 1, this is carbon 2, and carbon 2 has an ethyl group here like this, and that is connected with oxygen. There is hydrogen here. This is connected with C double bond O here, and this one. This is how it is connected. And you know that this will try to attack here, this will try to break here, and this will try to break here and make a double bond here. Done. The other way around of writing is I can keep 3 here, okay, 4 here, 1 here, 2 here. So this is, uh, 2, okay, and 3 here, correct? 2 and 3 here, and sorry, and this is 3 here, 2 here, correct? And on 2 we have 1 here, and this is 4 here, 1, 2, 3, 4. And hydrogen is present on 3, oxygen is connected on 2, which is connected to a double bond O here this way. So now you notice that this oxygen will take H plus from here, this will push here, this will push double bond here, correct? Now this is one intermediate, this is one intermediate, correct? Now in both of, both these transition state, in this transition state, here there is a hydrogen and ethyl, both of them are on the same side, but the repulsion will be minimum. Here there is a methyl and methyl, so repulsion will be maximum, correct? And if two groups are exactly like this, one below the other, I mean one beside the other like this is called eclipsed form of a conformation. And this eclipsed form here suggests that there are two methyl groups adjacent to each other, and that will have more repulsion compared to one ethyl and hydrogen. Here they'll have less repulsion. So therefore, the more substituted form to get into an alkene is rare. The less substituted group converting into an alkene is more observed. That's why Hoffman is major here. This part is clear? Right. Next, when it comes to elimination type of reactions, only these are the ones which you have it in syllabus. Okay, clear beta? What are the types we learned? E1, E2, E1-CB, isn't it? EI. Okay, these are the main four types of eliminations we should know. Now coming to the substitution type. Within substitution, there are two types. One is SE, that is electrophilic substitution reactions. The other one is SN, which is nucleophilic substitution reactions. Got it? Uh, One second. So now coming to this SN part of it. Here, substitution of nucleophiles. Okay. Firstly, there are some basic terminologies you should make clear before going into substitution reactions. What exactly is nucleophile? Anything which carries a lone pair and which attacks the delta positive charged nucleus like carbon, not hydrogen. It should not attack H plus. The minute it attacks H plus, that means it is defined as base and not as nucleophile. Okay, clear beta? Now, strength of a nucleophile decides which type of mechanism you should go for. Whether it will go for SN1, SN2, SNI, all of this depends upon what is the strength of your nucleophile. The measuring of strength of nucleophile is called as nucleophilicity. Okay, and in general, you'll notice that nucleophilicity, that is the strength of a nucleophile, is directly proportional to the basic character if you are operating in a periodic table, if you are comparing in a periodic table from left to right. If you are comparing left to right, the nucleophile is directly proportional to the basic character. Okay. And you would notice that here, when it comes to acidic character, I mean, when it comes to acidic strength, left to right, you know that acidic strength increases. And in left to right, electronegativity is the main factor you will notice. Got it? So if the electronegative difference is more, I would say it is more acidic in nature. So HF is more acidic compared to water, compared to ammonia, compared to CH4. Okay. And relatively, what would happen to its basic strength now? It will be exactly opposite of that. That is, this will become CH3 minus, NH2 minus, OH minus, and F minus. That will be the basic strength. Okay. Then what will happen to the nucleophilic strength? Nucleophilic strength follows the same as the basic character. That's why CH3 minus is a strong nucleophile, then NH2 minus, OH minus, and lastly F minus. Okay. But when you go down the group, you know that acidic character increases down the group. HI is stronger acid than HBr, HCl, and HF. Here you will not compare electronegative difference, rather you will compare bond dissociation energy. The bond dissociation energy of HI is less, so it will act like a better acid. So it is easy to break. Since it is easy to break, you will be making it a strong acid, which means the I minus is the weakest base. And HF being a weak acid, F minus is the strongest base. Correct? Now this will be the strength of, this will be the comparison of basic character. Now nucleophilicity is directly proportional to basic character as long as the solvent is polar aprotic or non-polar. Okay, beta. Now, what are aprotic? I just told you what are aprotic. That is, they do have a dipole moment, which is greater than zero, but they do not have a polarized hydrogen. There is no polarized hydrogen here. There is no acidic hydrogen here. Ethers, ketone, DMSO, DMS, THF, TMF, right? These are all, wherever you see, these are all what, beta? Polar aprotic solvent. Non-polar are the ones whose dipole moment is completely zero. Okay. Now, if you are choosing a solvent which is non-polar or polar aprotic, in both these cases, you will see nucleophile is directly proportional to basic strength. But if you are comparing, right, polar protic solvent, then nucleophile is inversely proportional to basic strength. That's why you will notice that nucleophile in polar protic solvent will be opposite to that of the basic strength. But in polar aprotic or non-polar or gaseous state also, I'll put that also, or gaseous state, or gaseous state. In this case, nucleophilic strength will be decreasing down the group. Got it? The logic follows even with the group 16 also. In group 16, you know that OH minus, HS minus, HSC minus, these are the bases. So this is a weaker base, but a stronger nucleophile in polar protic solvent. Correct? And arsenic AsH2 minus is a weaker base, but a stronger nucleophile in polar protic solvent. Okay. Now, you might wonder why is this happening? See, when it comes to polar protic solvent, suppose if at all I add fluorine F minus in aqueous solution, right? There is F minus in aqueous solution, and I'm comparing that with I minus in aqueous solution. Okay. Now, suppose there is a carbon positive weighting here. Here also there is a carbon positive weighting. So F minus here is a nucleophile, I minus is a nucleophile. Both of them are trying to go and attack carbon here. Both of them are trying to go and attack carbon here. Okay. Problem what happens is in case of F minus surrounds heavily by water molecules. Why? F minus is smaller in size. Since F minus is smaller in size, lot of water molecules will surround it. Correct? And this will have positive. All of this in water molecule dipole moment, we will have positive and negative here. So negative, 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 negative. Right? This is how they get surrounded. So what happens? Carbon plus is waiting, but fluoride to reach here will take lot more time. So this will become slow. Okay. But when it comes to I minus, correct? I minus will have hardly some water molecules around it. Correct? So if this has to reach to the carbon positive, it will reach much faster. Okay. Now this size difference only comes in polar protic solvent. In polar aprotic solvent or non-polar, the size is normal. Iodine is always bigger, fluorine is smaller. So always fluorine acts as a better nucleophile in those cases. Okay. Right. So check it out. If you notice, nucleophile of the same connecting atoms. So you can see if oxygen is the same atom which is acting like a nucleophile here with a charge on it, then how do we compare the groups around it? So what do you check out? You will check out which has a resonance and which does not have resonance. CH3O minus does not have any resonance. This has O minus will have resonance with benzene. Correct? So this lone pair is less available. This is more available. So which is a strong nucleophile? This one is a strong nucleophile. This one is a weak nucleophile. And in fact, basic character also depends on the same factor. So nucleophilicity here will be same as basic character. Okay. Next, If you compare these oxygens here, they all are being derived from these acids. You know that CH3OH is an acid, PHOH is an acid, RCOOH is an acid, RSO3H is an acid. Now, if you compare the respective pK value, this is around 15.5, this is 10, this is around 4, and this is -5, which showcases that RSO3 minus is a very strong acid leading to a very weak base, while this is a very weak acid leading to a very strong base. So if you are comparing different functional groups, then you can directly say that nucleophile will be directly proportional to the basic strength. Basic strength, okay? So more the basic strength means more is the nucleophilicity. Done, beta. Next, steric factors. See, nucleophile will always be inversely proportional to steric factor, and that makes it inversely proportional to basic character. Check out these cases. These are all alcohols, and they become alkoxide bases after removing H plus. Now, in this case, this is the strongest base because it is coming from a very substituted alcohol that is the weakest acid. So that makes it a strongest, that makes this as the strongest base. But when it comes to nucleophilicity, it is exactly opposite. Reason being bulkiness. Now, bigger the molecule becomes, it becomes very, very difficult for it to orient towards carbon and make a bond with it. Therefore, this would act like a better nucleophile than this, and then third butoxide. So much so that third butoxide, acts as, sorry, acts as, okay, nucleophile only in the case, only in the case where E2 is not possible. Got it? Only in the case where E2 is not possible, then only we can use that as a nucleophile. Otherwise, it will always act like a base and it will always give you E2. Next thing is about leaving group. Now, substitution reaction means what, beta? Substitution is you have something like R and a leaving group here, like this. R and a leaving group here, correct? And then there is a nucleophile here. This is a nucleophile. And nucleophile is attacking R, this leaving group is going. So eventually product what you are getting is Rx and leaving group with minus charge. No? So leaving group is always a conjugate base. Leaving group is always a conjugate base. Okay. And if that base is weaker, it will leave the molecule very easily. And if the base is stronger, it will be a weak leaving group. Got it? And that's what you will notice here. Out of these four, iodine is the weakest base. That's why it is a best leaving group. So iodine, Br minus, Cl minus, and F minus. This is the ability of leaving groups. Okay. And out of these three, we can say that these three are good leaving groups. These three are good Lg. While F minus is a poor leaving group, which we have learned earlier as well. Okay. Next. If you notice this one, CH3 minus PHO minus, just now we have learned that this is being a weakest base. That's why it is a good leaving group, right? So much so that this one is a, excellent leaving group, excellent leaving group. This one is good leaving group, and these two are poor leaving groups. Got it? Next. N2C2 OTS, ONS, OBR, and OF. All of these are super leaving groups. Super means very easily they can leave. None beta. These are all super leaving. How it is? Check out one by one. If N2 plus is connected to an alkyl group, you remove this bond, you will directly get N2 gas. This will become CH3 plus. In fact, a nucleophile is not even needed to make this reaction, which means just by maybe shaking the solution in the molecule, you'll immediately see nitrogen gases coming out. Got it? That easy to remove N2 gas. So it's one of the excellent leaving groups. Same case with carbon monoxide. Okay, if you shake this solution, immediately you will see carbon monoxide gas will come away, CH3 plus will form. And you know that CH3 plus is not even a stable carbocation, yet it will form. Okay, next. OTS. OTS means it is a toluene. This is benzene plus methyl group. Is methyl present? What do you call toluene? This part is toluene. This one is sulfonic acid. It is coming from sulfonic acid, correct? So that is why it is read as toluene sulfonyl ion, right? In short, it is called as tosyl. Tosyl. And how do we abbreviate it? OTS. Okay. Similarly, this one is instead of methyl, you have nitro. So taking the same analogy, you call it as nosyl. Okay. That's why OTS. If you have bromine, brosyl. Clear, beta? And this one is an exception. This is called triflate. This is called triflate. And all of these are excellent leaving groups. Got it? And OAC is relatively okay leaving group, not very good or bad. Okay, acetate. So again, see, these are all relatively good leaving groups. These are very poor leaving groups. Okay. Now, generally in a chemical reaction, this is something which we need to observe here, that if there is a leaving group like OH minus here, I'm pushing Cl minus to this, trying to remove OH minus. Now, after the reaction, you compare these two species, this one versus this one. Between these two, which is stronger base? Obviously, OH minus. Cl minus is a very weak base. It is coming from a very strong acid. So, a weak base can never generate a strong base. Therefore, this reaction will not happen, but the reverse can happen. That is, an alkyl halide can be easily replaced by OH minus, removing this Cl minus. Thereby, you will get this compound. Clear? Next, if you have an ethanol reacting with H plus, you will get this ethyl with OH2 group. And then if a chlorine is been added to remove this OH2, you will get ethyl chloride and H2O, which means this reaction was not otherwise possible to make it, to make the alkyl halide forming. What I did, first I made that OH into OH2 plus. And now OH2 plus is a very good leaving group compared to that of chloride. So now relatively this is a stronger base compared to water. So this reaction happens easily. And if you have an alcohol and you react with tosyl chloride, TSCl is tosyl chloride, then this H and Cl will go away and you will get this as OTS. OTS. And if you react that with Cl minus again, because here first HCl will go away, okay, and then if you react with Cl minus again, the Cl minus will connect, OTS will go, and you'll get ethyl chloride and TSO minus. Okay. Now, there are many type of nucleophilic substitutions: SN1, SN2, SNI, SNNGP, SN1 prime, SN2 prime. Like this, we have lot of substitution kinds. Let us start with SN2 kind now. Okay. SN2 is a single step reaction with no carbocation and no intermediate present in it. Got it? It is a single step with no carbocation and no intermediate present in it. Okay, that is a basic idea we should have. Got it? So check this out. Suppose if you have a methyl chloride reacting with OH minus, OH minus will go attack here, Cl minus will be relieved. That's how you'll get this product. And does it logically make sense? Yes, it is, because this is a strong base and this is a weak base. So you're trying to remove a weak base and substituting that with a strong base, which makes sense. How does this reaction proceed? While chlorine is leaving from one end, on exactly from the opposite end in their sigma star orbital, this is a sigma star orbital. In that sigma star orbital, OH minus will attack and Cl minus will go. Now notice this transition state. In this transition state, you are getting a trigonal planar like this here. This is a trigonal planar, right? With one OH above and one Cl below. So what is it? Trigonal bipyramidal. This is like a pyramid here and it is like a pyramid on this side. So it is a trigonal bipyramidal transition state. Trigonal bipyramidal transition state. Okay. So what you would notice here is that Cl is going, OH minus is attacking on it, correct? And that's how you will see the reaction happens. Now suppose instead of these hydrogens, if there are any bulky groups here, now these bulky groups will repel this OH minus, thus decreasing the rate of reaction. So rate of reaction is inversely proportional to the steric hindrance across around the leaving group. So methyl chloride will have the least, then some kind of crowding will come across ethyl, then isopropyl, then tert-butyl. So you notice that methyl 1 degree, 2 degree, 3 degree. If you compare SN2, it is more prominent for these two cases. Clear, beta? Next, rate of SN2 also depends upon bond dissociation energy. So if you notice the bond dissociation energy, CX bond, if it is weaker, the rate is stronger. So rate is inversely proportional to bond dissociation energy of CX bond. So larger the CX, more the CX bond dissociation, right? Less will be the rate here. So fluorine, breaking the fluorine bond becomes very difficult. So usually fluorides does not give SN2. Chloride, bromide, and iodine will give SN2. And out of that, iodine is more than bromine than chlorine. But while comparing this, all alkyl groups should be same. Now, rate of SN2 depends upon, what kind of a group that is present across it. Okay. So at this alpha position, there is a leaving group. In this case, there is chlorine. And then you have a C double bond O adjacent to it. Now, what is the advantage of that is this one. Suppose if you have chlorine leaving from here, there is a chlorine leaving from here, and this is its sigma star orbital. Adjacent to that, if you have a double bond O here, let's say there is a double bond O here. Double bond O will also have a sigma star orbital, sorry, pi star. This will have a pi star orbital. Okay. Now, when nucleophile is coming across here, you will have lot of emptiness around it. It is like a damp area here. Got it? And because of this damp area, nucleophile can attack much faster. So here that will become the fastest moving group here. Got it? That's the reason why if you have an alkyl group here, alkyl chloride group here, adjacent to that at beta position, if you have a double bonded group, that will make the rate, much faster. Got it? Next is, if the chlorine is leaving, similarly, here you notice that we have carbon, correct? And then we have chlorine leaving from here. Chlorine means this is the actual orbital of carbon and this is the orbital of chlorine. This is the, let's say, chlorine orbital. This is chloride orbital, okay? Now, adjacent to that, we have oxygen connected and oxygen has its own lone pairs. Oxygen has its own lone pair here, correct? Now, when this is sigma star orbital, and that is where the nucleophile is trying to attack, correct? So, before the nucleophile can come, this lone pair will help to fulfill the orbital with electrons so that it can facilitate the leaving of Cl minus. And that's why the rate will be much faster in this case also. Got it? So, adjacent to leaving group, if you have a lone pair carrying group, the rate drastically increases. So therefore, you would see this exceptionally high. After that, the next high SN2 is for this one. After that, same logic. Instead of now lone pair, now you have a pi bond. So benzyl will always react faster. Then we have 1 degree, then allyl, then 1 degree ethyl, 2 degree, then 3 degree. Okay. So this is the rate of SN2. This is the rate of SN2. Clear, beta? This sequence has been asked so many times in exams. May it be JEE mains or advanced, it has been asked many times. So this is something which you need to, without any confusion, you should almost like mug up so much that you should not have any confusion in identification of any side of it. Okay, exactly in the same line. You should remember. Okay, next, groups which never use SN2. First, tertiary, very difficult to use SN2 because of huge crowding. Then a tertiary kind of a group, but with a bridge position. At bridge position, the sigma star is inside the bridge, right? It is like this hut, and inside that hut there is a sigma star. So nucleophile cannot come into that hut. So therefore here, any kind of bridged positions you cannot have SN2. Next, there is an vinyl chloride. Vinyl chloride, chlorine is always in resonance with this pi bond. Therefore, it becomes very challenging to break this bond. So it is not a good leaving group because now chloride is involved in resonance within the molecule. Same logic applies to phenyl group also. So this chloride is involved in resonance with the phenyl group. Okay. And in three-membered ring, you will notice that if you have to, this is how this sigma, see in three-membered ring also, I'll show it here. Okay. This side is the chloride present and sigma star is present here. Correct. And this is side is hydrogen. Now, if a nucleophile is coming close to this one, first of all, these groups are very close to it. That itself is a problem. Second of all, if you remember, whenever the nucleophile has to attack, it has to take it as a trigonal shape, right? But here, what is the angle? 60 degrees. I require to make it as 120 degrees angle so that the chlorine is going, nucleophile is attacking. This is how it will happen. So, can this angle remain 60? No. That means if nucleophile has to attack, this bond has to break. Correct? Therefore, substitution is not possible due to the transition state which it cannot achieve. Secondly, this is an alpha position, but at beta position there is huge crowding. Alpha is not crowded, but the beta is highly crowded. Even if beta is heavily crowded, SN2 is very difficult to take place. So these are also the cases which are very frequently asked in JEE, that which of the following will not give SN2. Okay, right. Notice that. Next. If you notice the attack of nucleophile from the backside, a chiral center will undergo inversion. For example, if there is an R group here, OH minus will always attack from backside to sigma star orbital, removing this chlorine. When it attacks from backside, this D will come to the other side and thus this will become the product. Now if you notice the configuration, if this was R, this will become S. This type of an inversion is called Walden's inversion. Walden's inversion. Okay, beta? Any doubt with SN2?
No, sir.
Next, let us talk about SN1. SN1 is a multi-step carbocation forming group with a rearrangement possibility. And to make a carbocation, usually the groups has to be more bulkier so that it can get stabilized by hyperconjugation and inductive effect. So if I take a tertiary chloride and react with water, you will get an alcohol and Cl minus coming out. This would happen, this is the overall reaction. This overall reaction happens in two steps at least. First step is removal of chloride. You remove this chloride, you will get a positive charge here. And that is the rate determining step. And then once you get that positive charge, okay, water would attack on it and get an alcohol. This is a fast step. Since this is a slow step, if you notice the rate of SN1 here, sorry, I have not written here, I'll write down here. The rate of SN1 here will be equal to some constant into, alkyl halide raised to power of 1. So that is order is 1 and molecularity is also 1. There is only one molecule involved in the slow step. Okay. And rate of E1 depends on stability of carbocation. More stable the carbocation, more is the reaction that can happen. And rate also inversely proportional to nucleophilic strength. More stronger the nucleophile, lesser the fact to get carbocation and E1. Okay. Usually, SN1 and SN2 both will be same as much as bond dissociation energy is concerned. So, rate will be inversely proportional to bond dissociation energy of Rx. Okay. And iodine is more easy to break compared to bromine compared to chlorine. This will always be same in SN1, SN2, E1, E2. Always it will have the same logic. Okay. Next. If you compare the rate of the reactions here, the highest rate will be for the more stable carbocation. The most stable carbocation is octet completed carbocation. That means if you remove this chlorine here, gets a positive charge, lone pair will immediately make it stabilized. This is octet completed carbocation. Next one is remove this chlorine, gets a positive charge. This is CPM carbocation, cyclopropyl methyl carbocation. This is OCC, octet completed carbocation. Next carbocation is aromatic, aromatic carbocation. Remove that chloride, it will become aromatically stable. Next one is resonance. In resonance, right, triphenyl will have more resonance than diphenyl. After that, you will have 3 degree, then phenyl 2 degree and 1 degree. Okay. After 3 degree, we will have phenyl group here. So pH CH2Cl, then greater than 2 degree, 1 degree. Okay. This is how rate of SN1 varies. Got it? Just like in SN2, we have noticed certain groups will not give. Here also very similar groups does not give. Even this will not give, this will not give, this will not give, this will not give because it will make an anti-aromatic, as well as this will not give because it is a highly unstable carbocation on that. Got it? So these are the groups which does not give SN1 reaction at all. Okay, beta. Next. If there is an attack of nucleophile from both sides, then you will end up getting a racemic mixture in general. That is, suppose if you have an, chiral center here, and then you are reacting with water, correct? Which means first I need to make a carbocation. So once it becomes a carbocation, now this is an empty orbital with a positive charge. You have phenyl here, methyl here, and hydrogen here, which makes the water to have a possibility of attacking either from the top of the molecule or from the bottom of the molecule. If it attacks from the top of the molecule, possibly you might have R configured. If it attacks from the bottom, it might have S configured. And what are the chances? 50-50% chances. Therefore, we end up getting a racemic mixture in this case. So SN1 drives via racemic mixture. Clear with the difference of SN1 and SN2? Okay. Here it is always feasible with weak nucleophiles. Now, weak nucleophiles as well as I don't have enough space to write. I'll write down here. Okay. Okay. Favorable conditions in this case are first weak nucleophiles. Weak nucleophiles means no charge, like water, alcohol, acids, right? These kind of cases. These are weak nucleophiles. Next one, polar protic solvent, like water, alcohol, acids, ammonia, these kind. These are polar protic solvents. Okay. So these two are highly favorable conditions for SN1. है clear beta? Right. Next one is SNI mechanism. Let us see what is SNI mechanism. If you take an alcohol, react with SOCl2, you will get alkyl halide, SO2 and HCl. How does this proceed? See, the lone pair present on oxygen will act like a will act like a base. It will attack on sulfur to remove one of the chlorines. So you will get this intermediate form. Okay. And now this carbon oxygen bond where it is like this is how the overlapping is. As the overlapping becomes weaker, from the same end the chloride present here will attack. Okay. If it attacks from the same end, so basically from where you have removed oxygen, you are attacking from the same end. It is like SN2 but attacking from the same side. That's why it is called SNI. I means internal. So it is attacking internally from here to here, removing from the same side. So you will get this as the product. Which means, suppose if you had an R configuration, you are reacting with SO2, SOCl2 in ether. Okay. Now this would make, if you take SOCl2, that will make this R configured to remain as R configured only. So it will keep it as a retention product. Clear beta? Next. SNNGP. Let us see SNNGP. SNNGP is about neighboring group participation. Okay. C3 and C5 positions have a lone pair, you know, carrying groups. If at all they have lone pair carrying groups, then you will see that NGP is observed. What is NGP? Suppose, check out, let me put it in this way. Suppose I have a chloride here, beta. I'm treating this with water. It is going via SN2 mechanism to get OH here. Let's say the rate of the reaction is R1. Okay. If the same reaction is being done, if the same reaction is being done, but this time at this position, I have a sulfur also present like this. This is a chloride here, correct? Sulfur as a lone pair here, correct? And I'll get the same product here, sulfur this way, okay? And let's say the rate in this case is R2. You know what you will find? R2 is 600 times greater than R1. This is what you will find. It's over. Object. How many might be there? So the rate in the second case is very high compared to the first case here. Clear beta? Now, such high rate is observed for this reason, that is NGP, neighboring group participation. Neighboring group participation is also known as an chimeric effect. An chimeric effect. Usually this happens when the third position and the fifth position in the chain from the leaving group onwards, if you compare the third position and the fifth position, if they are if they carry a lone pair on it, like in this case you can notice sulfur is carrying a lone pair, so that lone pair will attack here, removing this chloride, so you will get a cyclic structure this way. Got it? And then when the water attacks from the other end, breaking this bond, you will get this form here. Got it? Now have you noticed this is also an internal attack, but it is attacking from the opposite direction. So what is this one? This is an SN2 attack. This is an SN2 attack internally, but it is SN2. And now when the water is attacking back here, sulfur is breaking. This is also an SN2 attack. Correct? So basically SN-NGP is nothing but SN2 attack happenings 2 times. If SN2 attack happens 2 times, that is called as SN-NGP. Got it? So the overall reaction is, if this position was R configured, that will remain R configured only. The retention will take place. So therefore, if two SN2 attacks are happening on the carbon to lead the retention, that is called as SN-NGP. Okay. Next, check out what is SN-TD. One second. SN-TD is when you have an double bonded carbon. Okay. Double bonded carbon on which the attack is happening. Let's say some strong nucleophile like R minus. This is called Grignard's reagent. And in Grignard's reagent, I have R minus. If R minus is going and attacking here, this pi bond will move here, making it as O minus, and this R minus will attack on it. Correct? And once you get this form here, this O minus will push and Cl minus will be removed out, thus making this as the product. Got it? So what is this product now? This is the keto form which you will get. But during the mechanism, what has happened here? First, an addition took place, correct? And here, if you notice the hybridization, this carbon was sp2 hybridized. After the attack, it has become sp3 hybridized. And again, the oxygen has pushed here. So eventually, the chlorine was removed, getting back to sp2 hybridization again. So it went through a nucleophilic substitution, forming a tetrahedral molecule. That's why it is called SN-TD. TD means tetrahedral intermediate. Got it? And SN-TD, SN-TD is a addition plus elimination reaction. So that's why it is also been represented as SN-AE. AE means addition elimination. First addition, then elimination type. Clear with this part? Right. Okay. Now, this is the basic synopsis. First example is about leaving group. Check out the leaving group in these three and let me know if you have any difficulty in understanding. Ammonia gaseous state, water liquid state, and alcohol in H. Okay.
Good.
Understood? See the second case now. NO2 is a better leaving group compared to Br compared to methyl. So what will be the order of a leaving group here? This one is better leaving group than this, then this. Make sense? Next. Triflate is even stronger leaving group compared to NO2 compared to CH3SO3 minus. Okay. Next one here, based on the acidic strength. These are all the order of bases. This one is a very weak base. That means it is a very good leaving group. This one is a poor acid coming from a pure acid. So it is a very strong base. So it's a weak leaving group. Clear, beta? Right. Next. This one we learned that I minus is a very good leaving group as well as very good nucleophile. Hmm? CF3CO minus is a good leaving group because it is coming from a strong acid. So it is a very weak base. Yeah, right. Next, this is a note representing the complete idea about SN2 with figures, with the energy diagrams to understand what exactly it is going on through. What are the list of strong nucleophiles which will favor? What are the good leaving groups? What are the poor leaving groups, right? And next, which substrates will not give that as a synopsis I told you. These are all the cases which does not give SN2. Okay. And finally, what will happen to the rate of SN2 in all these cases? Okay. Now, how does the inversion happen? Walden's inversion. I've shown you pictorially with some examples, right? Now, this is the order which I told you, right? You know that this is exceptionally high, which I told you. This is a different case altogether, so don't worry about that. But after that, you can see lone pair carrying group, then methyl, isn't it? Then CH3Cl, then allyl. After that, 1 degree. This is the rate of SN2. Got it? Done with it? Right. Now, these are the uh, applications of SN2. First is Williamson ether synthesis, which means if you have something like RO minus, which is a strong nucleophile, and you react with alkyl halide, which is SN2 ready. SN2 ready means what? X has to be either of these three. It cannot be fluoride. Second, R has to be either 1 degree, 2 degree allyl or benzyl. It cannot be 3 degree vinyl, neo or phenyl, correct? This will not give SN2. So if these conditions are satisfied, you will see RO minus will go attack here, remove X minus. So that's how you'll get an ether. So this way you are producing ethers, and this ether synthesis is called as Williamson ether synthesis. Clear? Next. Check out this one. Ethoxide reacting with this one, but this is not SN2 ready, so that's why no reaction will take place. This is SN2 ready, so reaction will take place and you'll get this as the product, ethoxybenzene. Okay, just a second. Right, so that will become ethoxybenzene here. Now, these are the examples which have been asked earlier, so please go through it once. C to G. Check all of them. Just come back in a minute.
So can you explain the E1?
E, right, notice. This is a good leaving group and this is SN2 ready. This is a good nucleophile, strong nucleophile, so it has to attack. Now the BR is coming out of the plane. So when this attacks, it should go inside the plane. So that's what I have written. This is inside the plane. Okay. So this is OET, ethoxy group. Okay. Hmm. F and G are clear. Right. Okay. This is called retrosynthesis. That means if you already know the product, you have to guess what could have been the reactants. Got it? So if this is a product, what could have been the reactants? Obviously, these two should have been the reactants. Correct? If this is a product, which is a correct way, this is a correct representation, right? Suppose if at all you write it this way, that is CH3O minus is attacking on alkyl chloride. Will this give SN2 beta? No SN2. This will not give SN2, no, because this is not SN2 ready. So this is not a correct representation to get this product. This is a correct way of attacking. Okay. So this has to be the alkoxide and this part has to be the alkyl halide in this case. Okay. Clear? Right. So check out the retrosynthesis quickly. 3 to 8. Check out all the cases once.
Instead of Cl, could it have been any other good leaving
It
group?
could have been bromine, iodine, any of those.
Okay.
5 to 8 is clear.
No, so why is it not prepared?
Think
Why
about
can't
it. If you make any alkyl halide, okay, see, if I make any alkyl halide here, let's say, if I take this as an alkoxide, this has to be alkyl halide, correct? But that alkyl halide cannot be ready for SN2, no? But
right? Yeah.
same way, this phenyl chloride will not be ready, bridge compound will not be ready, correct? Third butyl will not be ready. Hmm?
Got it.
Clear? Hmm. Next, check out this H. Okay, here O minus will attack this one, Br will be removed. Since you are not breaking anything here, that configuration will remain the same. Okay. Same way, this O minus will attack here, Br will remove that configuration. This configuration will remain the same. Nothing will happen there. Done. Next, if you take any alkyl halide which is SN2 ready and then treat with any of these reagents. See, it could be sodium bicarbonate, NaOH, KOH, K2CO3, KHCO3, Na2CO3, calcium hydroxide, anything that is given, they all meant only one thing, that you are giving aqueous OH minus. And aqueous OH minus will be good for SN2 ready reactions. Okay. So you can see first reaction, this will go via SN2, right? Second reaction, between these two positions, you know that this is vinyl chloride. Vinyl chloride cannot make any substitution. This will be bromide. So this will again make it SN2. This will also be SN2 with the inversion. Here this is SN2 with the inversion. Bromine is being removed. OH minus is coming. Correct? Next. Check out all these cases. Aqueous. If you have aqueous KOH, remove this. OH will come. You will get, inverted form. And ATO minus, same logic. SH minus, same logic. Got it? All of these are good nucleophiles. Done? Now, note down this reaction, which is Finkelstein reaction. Finkelstein reaction is where one halogen is interchanged with the other halogen. Okay. Now you notice that this I minus is trying to attack on R, removing this X. So we will get this as Ri plus NaCl or NaBr. And what is interesting to notice is that NaCl or NaBr, both of them form precipitate in acetone, which means if you want to remove chlorine or bromine and replace with iodine, this is a best reaction. So this is called Finkelstein reaction. This is precisely used to ensure that the chlorides and bromides are getting precipitated. Hmm? So you can see A, B, C, D reactions quickly. All of these are Finkelstein reaction. Br is left, iodine is replaced. Br is left, iodine is replaced via SN2. Br is left, iodine is replaced via SN2. Br is left, iodine is replaced via SN2. Okay. Second one is Swartz reaction. Swartz reaction is the one where a halogen exchange is happening to prepare RF, alkyl fluoride. Got it? So you can see AgF, CO, F2, Hg, Hg2, F2, Sb, F3, all of these fluoride cases. You can remove this X and replace that with fluoride. Okay. And in DMSO is a solvent used. It would usually favor SN2, and nucleophilic strength is like this, right? Fluoride is more strength than chlorine. Just now we learned. Hmm? So which means you can replace the halogens, which is chlorine, bromine, iodine, with fluorine in this case. And again, AgCl, AgBr, AgI, all of them are precipitates. Same way, CoCl2, CoBr2, CoI2, they will form either a complex or a precipitate. So that's why they become very stable, leaving behind alkyl fluorides. Okay. Hmm. Right. Same logic. Check out these 5 cases here now. Swartz reaction.
Done, sir.
And next is, how does the reaction proceed with AgCN and KCN? In simple terms, Cn minus is called as ambidentate nucleophile. That means it has the ability to attack from carbon also. It can attack from nitrogen end also. Okay. Same way we have NO2, in which it can attack from oxygen end also and nitrogen end also. These type of nucleophiles are called ambidentate nucleophiles. When you take KCN or NaCN, they would have ionic bond with Cn minus. Metals have ionic bond with Cl minus. Therefore, C minus end will be a stronger or a better donor form. So that will attack, X minus will go, creating a nitrile or a cyanide in this case. But if you take AgCN, in AgCN this is a covalently bonded metal. So the lone pair is only present on nitrogen. So nitrogen is a better donor. So nitrogen will go attack here, remove this X. So thereby you will get isonitriles. So with AgCN, you will end up getting isonitriles. With NaCN, you will end up getting nitriles. Clear? Right. Next, check out Rx. If you react with NaCN or KCN, you will get alkyl nitrate. With AgCN, you will get alkyl isonitrile. The same logic applies to NO2 minus also. In NO2 minus, This is an ionic bond. So O minus is present, which is a better donor. That will attack. Here it is connected with silver. So nitrogen is a better donor. So that will attack. So this will end up KNO2 or NaNO2 end up getting alkyl nitrite, while AgNO2 end up getting nitroalkane. Correct? So please check this miscellaneous reactions ABCD quickly.
Done, sir.
Check out E2H.
Yes, sir. Done.
Right. Next, check out the reactions of alcohols. Hmm. Alcohols cannot be directly reacted with Cl minus to get this. Just now we learned it. Hmm. But there are other reagents. We can use PCl5 directly to react. The lone pair will attack on empty orbital of phosphorus. Chloride will come out. And again the chloride will attack from the back side, removing this group. That's how you will get alkyl chloride, and this will become POCl3. Correct? So this is the overall reaction. HCl plus POCl3 is what you will get. So the overall reaction is this: alkyl halide, POCl3 and HCl. Done, beta. Since the attack is from the back side, it is an SN2 mechanism. Alright. This is an important tip to understand that, see, whenever you have PCl5, correct? Whenever you have PCl5, these are the functional groups given. That means alcohols, ethers, acids, anhydrides, and esters. If these are the functional groups given, you always make this all connections with chloride, these all connections with chloride, and this will make POCl3. Done. That's an easy way to remember. Clear? So wherever you have this, remove this part, and you can remove, you can make this one together and this one together. Clear it up? Right. And in case if you have an aldehyde or a ketone, then addition will take place and two chlorides will get added. Got it? In case of aldehydes and ketones. Next, it's all the same. Yeah. SOCl2, I just told you that. How does the ethynyl carbon will go become SNI? Okay. This is about SNI reaction. Yeah. Check out these cases now. Cases are important in this case. Check. In which case, what is SNI? Please go through all of them. See, for this, I need to mention one thing here. Check out. If you have noticed here, Alcohol with SOCl2 is supposed to get alkyl halide SO2. But the minute you use pyridine, you will not get HCl. You will get pyridinium chloride. You will end up with a salt. Now, what is the role of it is this one. You know that alcohol O will attack here, then Cl will go. This is the intermediate which we get, correct? Once you get this intermediate, now pyridine has reacted with HCl to become pyridinium chloride. So more than internal attack, now the external attack of Cl minus will be favorable. So this will attack, this bond will close, Cl minus will be removed. So what we are getting? SN2. So the same reaction, just that if at all I use pyridine, it will become SN2. If without pyridine, it is SNI. Okay, beta? Right. So with pyridine is SN2, without pyridine is SNI. Now with pyridine, the reaction's name is called Darzon's reaction. Okay, just keep that in mind. It is called Darzon's reaction. Done. Finished? Right. So go through the reactions quickly.
None, sir.
Done with right. The last reaction is the one where I'll stop it now. Check. The last reaction, if you notice, there is an alkyl group here. Okay. Sorry, allyl. There is an allyl group here. So allyl alcohol, if you have, you are noticing that oxygen will attack on the sulfur here. But chlorine is not attacking here, it is attacking here because of a six-membered ring formation. Correct? And then the double bond is moving on to this new position. Now, instead of attacking this position, if the attack is on the other carbon position, isn't it? Then that mechanism is called SN2 prime. It is called SN2 prime. Got it? If where the living group is going, exactly if it attacks on the same position, it is called SN2. But if it is attacking on the allylic position, it is called SN2 prime. Okay, clear with this point? Right. Okay. So we'll stop it here, beta. So I guess you got an idea about the mechanism, what all things you need to